same time, it influences the inactivation of the catalyst. In this video, you will learn how to set up mathematical models to predict the time needed for the conversion reaction at a given temperature. And the models will show how this time changes if the temperature increases, realizing that the conversion rate as well as the inactivation rate increase with the temperature. Let's consider the homogeneous reaction of reactant A to product P. We selected a batch reactor for the reaction as an example. The reaction may follow zero-order kinetics, but it might also be a first-order reaction. The value of the rate constants and increase if the temperature is increased. The Arrhenius equation can be used to predict how the reaction rate constant is affected by the temperature. In this equation, you recognize the Arrhenius constant A and the activation energy of the reaction E in joules per mole. The gas constant R, is 8.314 joules per mole per Kelvin, and therefore the temperature T needs to be expressed in Kelvin as well. We get back to the batch reactor, in which the conversion of this reactant A into product P takes place. It follows a first-order kinetics. We can set up the mass balance for the reactant A, which tells us that the change in concentration of reactant A in time is equal to the conversion rate minus K1 times Ca. If the catalyst is not inactivated during the reaction and the temperature of the tank is controlled, K1 remains constant. By solving the mass balance, we are able to calculate how much time it takes to convert, for instance, 99% of the total reactant A. In this graph, the blue line predicts how the concentration of the reactant A decreases in time at room temperature. And if the temperature is increased from 20 to 30 degrees Celsius, the red line, you can see that the reaction runs faster, so the conversion takes far less time. But the catalyst might not be stable at the applied temperature in the reactor. If the catalyst is inactivated, the rate constant K1 will decrease, and that's because the rate constant is linearly related to the concentration of active catalyst that is present. The inactivation rate reaction generally follows first-order kinetics, with first-order kinetic rate constant for inactivation, K inactivation. The value of this rate constant, K inactive, will again depend on the temperature. And yes, Arrhenius also applies here. The higher the temperature, the higher the rate of inactivation. So we have the first-order conversion of reactant A into product P, but at the same time, possible inactivation of the catalyst. The simultaneous inactivation will slow down the overall rate of the conversion reaction. You can predict this using a model that combines the mass balance for the reactant A with the mass balance for the catalyst. We can solve the mass balance for the inactivation of the catalyst and introduce the equation for the inactivation of the catalyst in the reactant balance. The mass balance for the reactant A can now be solved analytically, resulting in the equation shown here. And let's have a look at this equation. The first part is constant at a given temperature, but the last part tells you that the concentration of reactant A decreases exponentially with time at this particular temperature. If the temperature increases, this decrease will be quicker. It's best to try to do the mathematics yourself. Well, here you see the change in concentration of the reactant A in time. The solid line in the graphs depict a decrease in concentration in case you use a stable catalyst like the ones you saw before. The dotted lines show what happens if the catalyst is inactivated during the conversion reaction. For this example, you see that the blue lines show that the inactivation at 20 degrees is marginal. A small increase in temperature, though, to 30 degrees Celsius, as shown in red, obviously has severe effects on the catalyst. When the catalyst is stable, the reaction is completed within an hour, but if the inactivation of the catalyst is accounted for, you see that even after 3 hours, you still only converted 80% of the reactant. I hope I did not frighten you too much with the mathematical modeling, but I do hope that you recognized how powerful these mass balance-based models are to predict the overall reaction rate if simultaneous conversion and inactivation occurs. Imagine that heat may be generated during the reaction and that the temperature increases exponentially. That has very large effects. Better learn also how to design a good cooler for the reactor tank, isn't it? See you soon.